Alright, for this segment we are going to look at another application of integration. So if as you know, if you are given a function of x, we can find the area under the curve A to be just the integral of the function of x with respect to dx from A to B. But let's look at another application where, let's say, we can revolve this area about the x-axis. Okay, so here we will have what we call a solid, and because it is basically just this area right here, and then it's revolved around the x-axis, we may call this solids of revolution, because this area is revolved around x-axis. It becomes a solid. So in this problem we are going to find out, if this is a given solid, what is the volume of the solid. Okay, and then the next thing we want to find is the surface area, okay, of this solid. If this static pictures is not really clear for you, let me show you a few animation which probably will make you understand what we are looking at better. Let's say we were given a function, a simple function of fx, which is a constant. Right now it's fx equal to 10. Okay, and then if we revolve that around this x-axis here, we'll get something like this. So this is a solid of revolution, which we know as a cylinder, a simple cylinder. Okay, and everyone knows, I think probably you have learned about this in your high school mathematics, the volume of a cylinder, okay, is basically the area of this circle here, 2 pi, oh sorry, not 2 pi, it's pi r squared and times the length of the cylinder. So in this case, r here will be the distance from here to here, or in this case the distance from here to here, and then the length is of course here to here. Okay, all right, I think we can think of I think this is the same if we are working with a disk as well. The disk, you can say, if you're given a disk like this, okay, all right, so let's say this is the thickness of the disk. Let's name that thickness with small l, okay, and then the radius of that disk is r. The volume of that disk is similar, has a similar form like a V cylinder. Now why I'm telling you this is because this is going to be an important tool in trying to find volumes of any arbitrary shapes, especially volumes of solids of revolution. I'm going to show you another example. Let's say you are given another function like this, okay, which crosses at 10 and crosses the x-axis at 20. If you revolve this, if you find the area of under the curve and then you revolve it around the x-axis, you are going to get basically a cone. Yes. Another example, let's say you have a function like this, okay, which describes a almost a semicircle here. And if you calculate the area under this curve and then you revolve it around x-axis, you're gonna get something like this, which is basically the sphere. Now these are the three solids of revolutions that I've showed you, are simple shapes, you know, cylinders, cone and spheres. Now we can also look at weird shapes like this. For example, you have a function that looks like this, whatever that function is, and if you take the area under the curve, okay, and revolve it around the x-axis, you're gonna get something like a vase. Okay, so in this case, calculations of volume is not as easy as a cylinder, as a cone, or as a sphere. So how are we going to do this? Well, with what you have learned so far in calculus, it's easy to do this using the skills, the skills that you have learned in integration. So the idea is, if you revolve this area under the curve around the x-axis, you're gonna look something like this. So the way we're gonna do this is we slice these solids into thin discs, into many thin discs. Okay, and we've learned before that the volume of a disk can be obtained by pi. We multiply that with the radius of that disk squared and times the thickness of the disk, okay, small l. Now we can use the idea of slicing these solids into many disks and then find the volume of each disk and then add them up all together. Okay, so probably we're gonna have I don't know, many disks, maybe 100, maybe 1,000 disks, or maybe you know, 10,000 disks. All right, but the point is we want to make the concept clearer on how to find the volume of the solid by slicing it into many disks. The more disks, the better the more accurate our calculation of volume. So the idea here is this: how do we find, for example, how do we find this R here? How we determine this R for each of these disks? Okay, and how do we find the L, which is the thickness of each disks? All right, so what we can do is, basically, I'm just going to give you an idea so that the mathematics later on will be clearer for you. So for one thin slice of disk, okay, here, okay, let's say disk 1 here, okay, 1 being here. So we know it's pi. So what is R? R is basically the distance of this point here to the x-axis. So what is the distance? Basically that distance is f of x at that point. Okay, so it's basically here at that point. Let's say this is x asterisk, so the value here is f of x asterisk. Okay, so now for this slice we need to know the disk number 1, okay, and then the whole thing will be squared. Now that took care of the radius of the disk. What about the length? So the idea is we want to keep the length uniform. Okay, draw our calculations. So you might choose, let's say, from B to A here. I'm talking about this B here and A and B here. So if you want to equally slice the solids with 100 slices, so the thickness will be B minus A, the length of this, divided by 100. Okay, so if you have more discs, then this value will be thinner and thinner. Okay, so let's say we don't decide how many slices, but we just say it as small changes in x. So that means from x asterisk I, for example, to x asterisk I plus 1. Okay, the distance between these two is delta x. Okay, so and then we have this. So remember, you need to do this for not only disk 1, but you have to do this for disk 2, disk 3, 4, and so on, depending on how many disks you wanted. So you might go to infinity, okay, approaching infinity. So which means that the volume of the solids, the whole thing, will be just the summation of all the thin slices. Okay, summation of all this. All right, so well, that looks like a hard thing to do. Well, if you see this, the next slide, it won't be too hard. We've seen that how we go from here to here, and how we come up with this calculation of volume is basically the same as before. What we are doing here is we got pi here, so this is the pi, and this is the r squared, remember? Okay, this is the pi, this is the r squared, and this is the thickness of the disk, thickness of each disk, L. Okay, so it's a summation, so n will approach to infinity, which means that the amount of disks approach infinity, and the thickness of each disk is approaching 0. It means really thin. But if you're doing this, if you're doing well, numerical integration, this might be useful. But since we know some of our calculus, this can be simplified into just this. Okay, the volume of any solids of revolution described by the function fx, whatever that function may be, you know, you can use this formula right here: pi times the integral of the function here, whatever function that is, squared dx, with respect to dx. So let's say you have a function here described by x squared, and you need to for example, you need to you are cutting that function up until here, number at x equal to 2, and then you revolve that around the x-axis. You're gonna get something like a shape of a trumpet, yeah, something like this, I think. Okay, so what is the volume of this shape? Okay, so let me use different color. Red, dark red, it's not too nice. Now we've seen the formula. The volume is just equivalent to pi multiply by the, well, that's the interval, and then the function squared dx. Okay, so in this case the interval is from 0 until 2, so we just put this here, and then our function is x squared squared dx. So what we got here is 0 x to the power of 4, okay, dx. So next thing you need to do is just evaluate this integral and evaluate it between the interval 0 and 2. So if I'm not mistaken, this will be equal to that, and you need to evaluate this from 0 to 2, and then you'll get your answer. Okay, all right, so now let's think about this one. So my question here is, let's say you have a function is described by e to the power of x, and then you want to find the solids of revolution not revolving around x-axis but around y-axis. How are we going to do that? And let's say you want to revolve from 2 to 5. Okay, here only this part, find the area of this part. Okay, well, now this is kind of tricky, because from before, if it's from let's say if it's from 1 to 2 for 1 to 1.5, for example, in here. So this is easy. You can just take this formula right here. Okay, from 1 to 1.5. Okay, and then what fx just now, that's the f of x squared and the x, and then find the answer here. But now we're trying to find the solids of revolution when it is revolving around y. Okay, so I think what you need to do here is find the inverse function. So you know y is equivalent to e to the power of x. So x will be equivalent to natural log of y. Right. Okay, now we do that, we can put this here. Volume in this case will be pi, okay, from 2 to 5. So whatever that is. So right now it's function, inverse functions of x. Or in this case, let me make it clear. I think it will be clearer if we do it like this. Okay, f of y with respect to dy. Okay, so what is f of y? Hint, hint. Okay, so between these four answers, which one do you think should be? If I were to revolve this solid around the y-axis with the interval defined like that. Okay, so I hope with those two examples and the formula that is given, and also how we come up with the formula, will help you in answering the engineering applications questions about finding volumes of solids. I'm going to show you two more formulas. Let's say you have a function f of fx from a with the interval from a to b, provided it's continuous. How to find the length here? Length, or the arc length. Okay, it's not so easy because, well, it's not really a straight line, so that's why I call arc length. How to find that? I denote this with a small s. The formula is this. So for example, let's say fx is defined as for example, let's see x squared. Yeah, so what is the arc length from a to b, for example? So it would be just, all right? So I need to find the derivative of x squared, and then square that, and then everything square root. Okay, so I know that this is 1 plus, if I were to differentiate this inside here, I will get 2x. Okay, right, and then I still need to square the whole thing, and then square root the whole thing there, and then this will become 1 plus 4x squared, square root everything. So evaluate this integral, and then you'll find the length of the arc length of this function from a to b. Another one is, just now we have tried determining on how to find the volume of this solid when this area under the curve is revolved around the x-axis. So what about the surface area? Okay, so surface area of the solid. Okay, so this is the formula given. So for example, let's say f of x, whatever, I'm just gonna pick x squared. I like this. Okay, so how to find the surface area of this solid described by the curve x squared. Okay, so in this case you just write down everything. Okay, fx in here is x squared, so x squared here times 1 plus I think we have done it before, x squared, differentiate that in respect to x, we'll get 2x. Okay, this whole thing is squared, dx. Okay, so now I think it's a bit more, I would say, messy. Okay, but this is the integral that you need to evaluate. Alright, so that is all for today. You've learned about 3 formulas and their applications in I would say applications of calculus in engineering. One is to find the volume of any shape that can be described by functions or area under the curve, which is revolved around an axis, its arc length, and also the surface area of the solid. So 3 important points which are going to be really useful for us in engineering.